Hi everyone, this is Majid Haidari. So today I will show you how we can design and simulate a voltage controlled current source using SaberRD. Actually, this tool allows us to combine analog, digital and system level component into one simulation. So for instance, in this picture you see FPGA, sensor, ASIC, so load. You see a mixed signal, analog and digital. So I will show you how we can start simulation a mixed signal. So first, let's look at the SaberRD capability. The first thing is multi-domain modeling. With Saber, you don't just simulate electrical signal. We can also include thermal, magnetic, and mechanical effects. All these domains are combined into one environment. So we see how they interact. So the next thing is the Saber has more than 30,000 models ready to use. We can model using MAST or VHDL AMS, or we can reuse SPICE model and even bring in C or MATLAB models. So this let us work at different level, simple behavior block or fully physics based detail. So also Saber connect with other tools like MATLAB, Simulink, and it support FMI, FMU. So this means we can exchange model with other simulation and link our work into a large system flow. So another topic is analysis of Saber. So Saber helps us to check robustness and safety. We can run parametric sweeps, Monte Carlo analysis, sensitivity analysis, and even support fault injection and standards like ISO 26262 and ISO 25192 for functional safety. So it's digital and analog synergy. So like as you see here, like I showed a voltage control current source design. We have like FPGA or microcontroller to generate a beta stream for us. We have a sensor, we have op-amp, like we have comparator logic, we have some other logic. So so for instance, we have D2 wire. So D2 wire convert digital pin transition into analog control signal, and then we have control to current, actually convert the unitless control signal into an electrical current. And so let's see how we can model this circuit. So I will show a demo of Saber in the next video, but in this video mostly I will focus on the concept. So here, as you see, like for the sensor, we have a sinusoidal signal, and for FPGA and microcontroller, we have a pulse. So these are our inputs. So now I will show you how we can model like with Saber, like how we can model a comparator logic with Saber. So how comparator logic works. So if Vin is greater than like VH, so the output goes high. So you can see the description of our comparator logics here. So I want to model this comparator logic with HDL language. So let's see. This is the VHDL AMS. So as you see, so when we are modeling with HDL language, actually it's a little bit different than conventional language. Like see, we can do the parallel analysis with HDL language. So as you see here, we model the op amp, we model the comparator. So like this block waits for any changes on enable V in above VH or V in above VL. So if something happened, then we have to see some if, else if, and like if logic. So you can see how we can model this comparator with VHDL AMS. So now this is the output of comparator logic. So exactly you can see the hysteresis behavior, you can see the VH, VL, and how comparator generate this pulse for us. So in the GUI of comparator, you access to change and modify this parameter like P offset, positive offset, and like offset in the negative port. So you can put the hysteresis. So this is the input of AND gate. So this one is generated by the microcontroller or FPGA, and this is the output of AND gate. So you can see because of this delay that we put for AND gate, which is around 1 millisecond, so we can see we have 1 millisecond delay in the output. So now if you look at the D2 wire, so D2 wire convert the signal to analog signal. So as you see here, this is a black pulse. So and the load, you can see the load here. So what you can see, you can see this load is followed our sensor signal, and then if voltage goes beyond the 3.2, then the feedback, this inverter goes to low, and then the output of AND goes to 0, and then you can see just we have RNC, so we have a discharging, and here we're charging, discharging. So you can see you can exactly monitor everything in Saber. Okay, now let's look at how we can set up an experiment in SaberRD. So in this case, we use a parameter sweep to automatically vary the load resistor, run the transient analysis, measure the RMS value, and plot the behavioral of load versus time. So let's look at how we can define an experiment. So as you see here, we change the resistor from 3 kilo to 10 kilo with 5 number of points, and with multi-core simulation to speed up the simulation. And then we have a transient analysis in 100 milliseconds. So we measured all signals here. So then we measured the RMS load and see what's the result, how the results looks like. So here is the result. So the top shows the waveform versus time for the load. So and here it shows the RMS versus different actually resistor value. So yeah, great. So also so in this step we can extend the experiment by adding a pass-fail condition. For instance, I put the test like if RMS load is greater than 1.6 is passed, below than 1.6 failed. So you can see the results. So this is great. So this makes it easy to verify design requirement during simulation. Instead of manually inspecting the wavefront, SaberRD can directly confirm whether the performance criteria are met. You know, yeah, great tools. I will show you how we can model and simulate so this current source in SaberRD in the next video. See you in the next video.